On a clear autumn night, away from city lights, you can see something that shouldn't be visible at all, a tiny, faint smudge of light hovering near the constellation Cassiopeia. You're looking at the Andromeda galaxy, a trillion stars located 2.54 million light-years from Earth. But what you're seeing with your naked eye is a lie, not in what's there, but in what's hidden. The true scale of Andromeda isn't just about numbers. It's about what those numbers actually mean when you try to hold them in your mind. We're talking about a structure so vast it challenges the limits of human comprehension, yet connects us to the deepest patterns of cosmic existence. If you enjoy these deep explorations of space, a quick like or subscribe would really help the channel grow. Get yourself comfortable. We're starting with something you can actually do tonight: finding Andromeda with your own eyes. Finding Andromeda begins with finding Cassiopeia, the W-shaped constellation that sits almost directly opposite the Big Dipper across the North Star. In autumn and winter, it rides high overhead in the northern hemisphere, 5 bright stars forming a slightly lopsided W, or an M if you're looking at it upside down, which happens naturally as it rotates through the night. Once you've found that W, let your eye drift down from the rightmost point of the formation, not straight down, but at a gentle angle toward the east. You're looking for the Great Square of Pegasus, 4 stars forming a large, nearly perfect square that dominates the autumn sky. Between Cassiopeia and Pegasus, roughly a third of the way from the W to the square, there's a spot where the darkness isn't quite uniform. It's not a star. Stars are points. This is something else, a soft, faint glow, almost like someone breathed on the night sky and left a small patch of condensation. If you look directly at it, it might disappear. Your peripheral vision often works better for faint objects. The center of your retina is built for color and detail, but the edges are built for sensitivity in low light. So you look slightly away and the smudge emerges. That's Andromeda. To your naked eye, it appears small, 1.5 to 2 degrees across the sky, which translates to roughly 2 to 3 full moons placed end to end. A modest smudge, easily overlooked if you don't know where to look. In 964 AD, Anas, the Persian astronomer Abd al-Rahman al-Sufi, described it in his Book of Fixed Stars as a small cloud. For centuries, that's what astronomers assumed it was. A cloud of gas and dust within our own galaxy. A nebula, something relatively nearby in cosmic terms. Just one more wisp of luminous material scattered among the stars of the Milky Way. But then came the long exposure photographs. When you point a camera at Andromeda and leave the shutter open for hours, allowing faint photons to accumulate on film or sensor, something extraordinary emerges. The small cloud expands, 5 to 6 degrees across, 10 to 12 full moons side by side. You might have heard the figure 30 moons. That number appears in older sources and has been repeated often enough to become common knowledge. But it comes from a misunderstanding of how to measure angular size. The true extent is roughly half that, 10 to 12 full moons, which is still staggering. This makes Andromeda the largest deep sky object visible without a telescope. Not the brightest. That distinction belongs to the Magellanic Clouds, but those are only visible from the southern hemisphere. For anyone in the northern latitudes, Andromeda is the champion of apparent size. Most of its light is too faint for our eyes to register, so we see only the bright core. The visible galaxy is just the beginning. The rest is there, waiting in the darkness, pouring photons toward Earth that our retinas simply can't catch. So we have a smudge that appears small but is actually enormous. This raises an immediate question. Where is it? How far away is this thing? Now, the answer came in the 1920s, and it changed everything. Edwin Hubble, working with the 100-inch telescope at Mount Wilson Observatory in California, then the largest telescope in the world, began photographing Andromeda with unprecedented clarity. He was looking for individual stars, not the collective glow of billions merged together, but discrete points of light, and he found them. More specifically, he found Cepheid variables, stars that brighten and dim in a regular, predictable rhythm. Some pulse every few days, others every few weeks. The period of that pulsation is directly related to the star's intrinsic brightness. A Cepheid with a 10-day period is intrinsically brighter than one with a 5-day period, in a relationship so consistent it functions as a cosmic ruler. As that relationship was discovered by Henrietta Leavitt in 1912. She worked at Harvard College Observatory, but not as an astronomer in the traditional sense. She was hired as a computer, a job title given to women who performed mathematical calculations and catalogued photographic plates for a fraction of what male astronomers were paid. She wasn't allowed to use the telescopes. Her job was to examine thousands of images of stars and record their positions and brightness. She examined stars in the Small Magellanic Cloud, a satellite galaxy of the Milky Way. Because all those stars were roughly the same distance from Earth, any difference in apparent brightness reflected a difference in true brightness. She noticed that the Cepheid variables with longer periods appeared brighter. She plotted the relationship on a graph, period versus brightness, and found a clean, elegant pattern. It was one of the most important discoveries in the history of astronomy, and it came from someone systematically cataloguing data, performing the tedious work that the field required but rarely celebrated. When Hubble identified Cepheids in Andromeda, he was using Leavitt's ruler. He measured their periods, calculated their true brightness, compared it to their apparent brightness as seen from Earth, and worked backward to determine the distance. His first estimate was 900,000 light-years. Later refinements pushed that number higher. Better measurements, better calibrations. The current accepted distance, 2.54 million light-years. At that number, 2.54 million, is not an estimate rounded for convenience. It represents decades of measurement refinement, calibration, and correction, and it holds. This was the moment the universe got bigger. Not physically, it had always been this size, but conceptually. Andromeda was not part of the Milky Way. It was not a cloud of gas within our galaxy. It was an entirely separate island universe, a galaxy in its own right, containing hundreds of billions of stars, sitting at a distance so vast that it defied every intuitive sense of scale. So we know Andromeda is a separate galaxy, not a cloud of gas. But that discovery immediately raises the question, how far away is it? What does 2.54 million light-years actually mean? The speed of light is just under 300,000 kilometers per second, roughly 186,000 miles per second, if you prefer imperial units. Nothing moves faster. It's not a speed limit in the sense of a posted sign that could be ignored with better technology. It's woven into the structure of space-time itself, a fundamental constraint on how information propagates through the universe. In 1 year, light travels 9.5 trillion kilometers. That's 5.9 trillion miles. We call that distance a light year, not a unit of time, but of space. The distance light covers in 1 year of uninterrupted travel. Multiply that by 2.54 million. The result is 24 quintillion kilometers, 15 quintillion miles, 24 followed by 18 zeros. This is the kind of number that doesn't mean anything to the human brain. We don't have the architecture to hold it. You can write it out on paper. You can perform arithmetic with it, but you can't feel it. It exists purely as abstraction, a placeholder for a distance so enormous that even attempting to visualize it is a kind of category error. The number is correct. The calculation is sound, but understanding it requires something we don't possess. So we turn to comparisons. Sunlight takes 8 minutes and 20 seconds to reach Earth. That's our baseline. The sun, the center of our solar system, the source of all energy that powers life on this planet, is 8 light minutes away. We could hypothetically build a spacecraft that makes that journey. We've sent probes to the sun. 8 minutes is within the realm of human comprehension. Proxima Centauri, the nearest star to our solar system, it is 4.24 light years away. That's already beyond anything we can currently reach with our machines, but the timescale is at least relatable. 4.25 years. A presidential term, the length of a college degree. We can hold that in our minds. Now, Andromeda, 2.54 million light-years. When the light you see tonight began its journey from Andromeda, anatomically modern humans didn't exist. Homo habilis, one of our early ancestors, was walking the savannas of East Africa, using primitive stone tools to butcher carcasses and crack bones for marrow. There were no cities, no agriculture, no written language, no concept of a galaxy. All of recorded human history, every empire, every war, every discovery, every thought that has been written down and preserved, represents less than 0.25% of the time that light has been traveling. We are seeing Andromeda not as it is, but as it was. The galaxy you observe tonight exists in a moment 2.54 million years in the past. Whatever is happening there now, stars being born, planets forming, perhaps even civilizations rising and falling, that information hasn't reached us yet. It won't reach us for another 2.54 million years. The present state of Andromeda is inaccessible, not because our telescopes aren't powerful enough, not because we lack the right instruments, but because the information itself is still in transit, crawling across the void at the fastest speed the universe allows. We can never see its present. The galaxy exists in a now that is forever hidden from us, always receding at the same rate we move forward in time. This is simply how reality works at cosmic distances. Simultaneity is an illusion. There is no universal now. There is only here and now, and everywhere else exists in our past. Every distant object you observe is a time capsule. The farther you look, the deeper into history you see. The universe has no shared present moment. Let's try machines instead of light. The Parker Solar Probe is the fastest human-made object ever launched. It's designed to dive through the Sun's outer atmosphere, using Venus's gravity to slingshot itself to incredible speeds. At its fastest, it reaches 700,000 kilometers per hour, 430,000 miles per hour. Fast enough to cross the United States in less than half a minute. Point it toward Andromeda and launch. It would take 3.9 billion years to arrive. That's nearly as long as Earth has had liquid water on its surface. When the journey began, life on our planet would be single-celled organisms. By the time it arrived, entire evolutionary epochs would have passed. Continents would have drifted into new configurations. Species would have emerged, flourished, and gone extinct thousands of times over. Voyager 1, launched in 1977, is traveling at 61,000 kilometers per hour, 38,000 miles per hour. It's the most distant human-made object, currently exiting the outer boundary of the Sun's influence, crossing into interstellar space, a triumph of engineering, and still transmitting data after more than 4 decades in the void. Point it toward Andromeda. It would take 44 billion years. The universe itself is only 13.8 billion years old. Voyager would need to travel for more than 3 times the current age of everything that exists. If we had launched it at the moment of the Big Bang, when space-time itself came into existence, it still wouldn't have arrived. It wouldn't even be halfway there. Imagine Voyager now, a tiny probe the size of a small car, drifting through the darkness between stars. It moves relative to the Sun, but against the scale of the galaxy, it's essentially motionless. A speck of metal carrying a golden record with greetings in 55 languages and samples of music from Earth, yet crossing a gulf so vast that it becomes a metaphor for permanence rather than travel. It will drift for billions of years, long after Earth has been consumed by the Sun's expansion, long after the Sun itself has cooled to a dark cinder. This is what 2.54 million light-years means in practical terms. Not a journey we might someday make faster, but a gulf that isolates galaxy from galaxy in time itself, and it will still be nowhere close to Andromeda. This is the distance we're talking about. Not a gap we could ever cross, but a gulf that isolates us in time itself. And yet, Andromeda appears large in our sky. Not large enough to dominate, but large enough to be visible without a telescope. 2 to 3 full moons to the naked eye. 10 to 12 full moons in a long-exposure photograph. That means something. If an object appears this size despite being 2.54 million light-years away, its actual physical size must be titanic beyond comprehension. The visible galaxy is just the beginning. The smudge you see in the night sky is only the core, the densest concentration of stars where the light is bright enough to cross that immense distance and still register on human retinas or camera sensors. The full structure extends far beyond what casual observation reveals. Spiral arms sweeping outward, a disk of stars and gas, a halo of ancient stars, and beyond even that, structures invisible to optical telescopes, but detectable through other means, ghosts of smaller galaxies consumed long ago, and something even stranger that we'll come to shortly. The distance kept us looking at a smudge for centuries. But once we understood how far away that smudge was, we could calculate backward, from apparent size to true scale. So, If we could cross that distance instantly, if we could step outside the constraints of light speed and simply appear on the other side of that 2.54 million year gulf, what would we find waiting? What does a structure this vast actually look like when you're standing inside it instead of squinting at a faint smudge from across the universe? We've established the gulf, 2.54 million light years, a distance measured not by our telescopes seeing farther, but by understanding what we were looking at when we saw it. A distance that makes even our fastest machines into monuments to futility rather than exploration. But here's what that impossible distance tells us. If something appears large in our sky despite being that far away, its actual size must be staggering. Andromeda spans 220,000 light years in diameter. For context, the Milky Way, our entire galaxy, containing our Sun and every star you can see with the naked eye on a clear night, stretches about 100,000 light years across. Andromeda is more than twice that width. The visible galaxy is just the beginning, but even just the beginning dwarfs everything we call home. It contains approximately 1 trillion stars. The Milky Way holds somewhere between 100 billion and 400 billion stars, depending on which estimates you trust and how you account for dim red dwarfs too faint to easily count. Andromeda is at least 2.5 times that, possibly more. 1 trillion is the current best estimate. A trillion stars, not a round number chosen for rhetoric, but an actual count derived from luminosity measurements and mass estimates. What does a trillion mean? If you started counting, 1 star per second, no breaks for sleep or food or anything else, it would take you 32,000 years to count them all. 32,000 years ago, humans were painting the walls of Chauvet Cave in what is now France. Agriculture didn't exist. Writing didn't exist. The wheel didn't exist. You would need to count continuously through the entirety of recorded civilization and back into the Paleolithic just to reach the end. A trillion seconds is 31,709 years. Let that sit for a moment. The total mass of Andromeda is somewhere between 1.5 and 2 trillion times the mass of our Sun. Most of that mass is stars, hydrogen and helium compressed by gravity into spheres hot enough to fuse atoms in their cores. But not all of it. We'll return to what else contributes to that mass shortly. For now, the point is scale. Andromeda is not just larger than the Milky Way, it is vastly, overwhelmingly larger. So if we could cross that distance, if we could step outside the tyranny of light speed and appear on the other side, what would we actually find? We would find a structure with anatomy, a core, a disk, spiral arms, regions of birth and regions of quiescence, a system in motion, held together by gravity and shaped by forces that play out over hundreds of millions of years. Start at the center. The galactic core is a densely packed sphere of stars spanning 30,000 light years across. That's larger than the entire central region of the Milky Way. The stars here are old, 10 billion years or more, and they're packed so tightly that the space between them shrinks to fractions of a light year. In our neighborhood of the Milky Way, the nearest star to the Sun is over 4 light years away. In Andromeda's core, stars are separated by distances you could cross in months, rather than years if you could somehow travel at light speed. Imagine standing on a planet near that core. The night sky would not exist as we know it. Darkness would be impossible. Even at midnight, the sky would glow with a perpetual twilight, not from a sun, but from the sheer density of stars surrounding you. Thousands of stars bright enough to cast shadows. Not faint pinpricks requiring your eyes to adjust, but actual points of light intense enough that you could read by them. The combined light from all those nearby stars would create a dome of soft reddish-gold luminescence overhead. You would never see true night. The psychological weight of that, of living under a sky that never dims, where the universe presses in with light from every direction, is hard to imagine. There would be no relief, no quiet, just the persistent glow of 100 billion suns, compressed into a region small enough that their light becomes ambient, a background hum of radiation filling every shadow. We are creatures adapted to darkness, to cycles of light and shadow. A sky that never dims would reshape not just vision, but psychology. This core, violent, dense, chaotic, is the gravitational anchor for everything else. At its very center sits a supermassive black hole, 140 million times the mass of the Sun. For comparison, the Milky Way's central black hole, Sagittarius A star, the monster at the heart of our own galaxy, is about 4 million solar masses. Andromeda's black hole is 35 times more massive. It's not the largest black hole we've discovered, but it's enormous by any measure that matters to structures on galactic scales. For years, astronomers thought Andromeda might actually contain two supermassive black holes orbiting each other near the center, a binary system left over from a past merger with another galaxy. Observations in the early 2000s suggested a double nucleus, two distinct bright points very close together. Yet it was an exciting possibility. Binary supermassive black holes should exist if galaxies merge as often as we think they do, but catching them in the act is difficult. They spiral inward over millions of years, radiating gravitational waves, until they eventually collide and merge into a single, larger black hole. But more recent observations, particularly data from around 2020, largely ruled this out. What looked like two black holes turns out to be one black hole surrounded by an eccentric disk of stars, a swarm of orbits tilted and stretched by past gravitational disturbances. From certain angles, the disk creates an optical illusion, making the nucleus appear doubled. It's one monster, not two. But the disk itself is strange, evidence of violence, of something that disrupted the orderly orbits and left behind this tilted, chaotic structure. Near the black hole, physics becomes extreme. Gas spiraling inward heats to millions of degrees, glowing in X-rays. Magnetic fields accelerate particles to nearly light speed, creating jets of radiation that blast outward perpendicular to the disk. Space-time itself warps, orbits precess, yet time dilates, paths that should be straight become curved. The black hole doesn't pull things in like a vacuum cleaner. It distorts the geometry of space so severely that all possible futures lead inward. Once you cross the event horizon, every direction you could travel in space points toward the center. You can no more avoid falling in than you can avoid moving forward in time. We've seen this now, directly. In 2019, the Event Horizon Telescope, a network of radio dishes scattered across the Earth, effectively creating a telescope the size of the planet, captured an image of the supermassive black hole at the center of the galaxy M87. Not Andromeda, but a similar object, 55 million light-years away, 6.5 billion solar masses. Yet the image showed exactly what theory predicted, a dark circle surrounded by a glowing ring of emission, where light from the accretion disk bends around the black hole's gravity and reaches us despite being aimed in other directions. The shadow of the black hole itself, the region where no light can escape, was visible as an absence, a hole in the universe. Andromeda's black hole would look similar if we could observe it with the same resolution. But we are seeing Andromeda not as it is, but as it was, 2.54 million years ago. Whatever is happening near that black hole right now, whether it's actively feeding or sitting dormant between meals, we won't know for another 2.5 million years. We are seeing Andromeda not as it is, but as it was. Even its black hole exists for us only in deep history, and the information is still crossing the void. Move outward from the core and the density drops. The spiral arms emerge, sweeping curves of light that make Andromeda recognizable in long exposure photographs. But here's the strange part. The spiral arms are not made of specific stars. They are density waves. This is not immediately intuitive. When you look at a spiral galaxy, it appears that certain stars belong to the arms, and other stars exist between them. It looks like a physical structure, like the arms are fixed features rotating with the galaxy. But if that were true, the arms would wind up and disappear over time. Galaxies rotate differentially, meaning stars closer to the center orbit faster than stars farther out. If the arms were made of specific stars, they'd wrap tighter and tighter with each rotation until they became indistinguishable from the disk. This is called the winding problem, and for decades it was a genuine puzzle. The solution is that spiral arms are not things but events. They are regions where stars temporarily slow down, bunch together, and then continue on their orbits. The density wave itself, the spiral pattern, rotates at a different speed than the stars. The pattern persists, but it's not made of the same stars over time. Imagine a circular highway where all the cars travel at constant speed. Traffic jams spontaneously form, regions where cars bunch together, slow down slightly, and then accelerate again as they exit the jam. The jam itself moves around the highway at a different speed than the cars. From above, you'd see a persistent pattern, a cluster of cars that appears stationary relative to the road, even though the individual cars are constantly entering and leaving the cluster. The jam is real, it has effects, it shapes traffic flow, but it isn't made of particular vehicles. It affects the cars passing through it, but it's not made of specific cars. It's a wave passing through the population of cars, reshaping their distribution without being composed of any fixed group. The pattern persists, the objects creating it change. This distinction between structure and the material that fills it is not intuitive. This is what spiral arms are. Stars enter the density wave, slow down due to the increased gravitational pull from all the other stars bunched together, linger for a while, and then exit on the other side. So while they're in the wave, the increased density compresses gas clouds, triggering the collapse that leads to star formation. New stars are born inside the spiral arms, hot, massive, blue stars that burn ferociously and die quickly. These blue giants, spectral types O and B, live only a few million years. That's so brief on galactic timescales that they die before they can travel far from the place they were born. They ignite, blaze brilliantly, and explode as supernovae while still inside the density wave that created them. An entire stellar lifetime, birth, fusion, death, contained within the wave that triggered their existence. This is why the spiral arms appear blue and bright in photographs. Not because blue stars preferentially gather there, but because blue stars are born there and don't live long enough to leave. And between the arms, the disk contains older, redder stars distributed more evenly. These stars, like our Sun, live for billions of years and have had time to drift away from their birthplaces. They fill the spaces between the spiral arms, creating a more uniform background glow that's harder to see in images because it's overwhelmed by the bright young stars in the arms. There's a particularly active region about 32,000 light-years from Andromeda's center, a ring where star formation proceeds continuously. Gas and dust accumulate there due to orbital resonances, piling up until gravity triggers collapse. Stars being born right now in that ring won't be visible to us for another 2.54 million years. We are seeing Andromeda not as it is, but as it was. The present state of that star-forming region, the stars igniting this year, this century, this millennium, is information still in transit, crawling toward us at the only speed the universe permits. The disk itself is vast but thin. At the location equivalent to where the Sun sits in the Milky Way, the disk is about 1,000 light-years thick. That sounds enormous. It is enormous, but relative to the disk's width of 220,000 light-years, it's paper-thin. If you scaled Andromeda down so its diameter matched the width of the United States, the disk would be about as thick as a sheet of paper. This thinness is maintained by rotation. The galaxy spins, and the angular momentum keeps most of the mass confined to a flat plane, the same way a pizza maker spins dough to flatten it. And Andromeda does spin, and stars orbit the galactic center at hundreds of kilometers per second. Near the core, orbital speeds reach 300 kilometers per second or more. Farther out, speeds drop but remain high, enough that the entire visible disk completes one full rotation approximately every 250 million years. One galactic year. This is the timescale on which the spiral pattern operates. Slow, persistent, vast. In the time it takes the Sun to orbit the Milky Way once, every civilization that has ever existed on Earth has risen and fallen. The last time the Sun was in its current position relative to the galactic center, dinosaurs had not yet evolved, so the spiral arms we see are not permanent structures, but waves passing through a sea of stars, temporary, beautiful, and always in motion. But mapping this rotation revealed something deeply strange. The outer stars, those located far from the galactic core, out in the dim regions where the density drops and the spiral arms fade, orbit far too fast. According to Newton's laws, orbital speed depends on mass. The farther you are from the center of mass, the slower you should orbit. This is how our solar system works. Mercury orbits quickly, Neptune orbits slowly. You can calculate the expected speed if you know how much mass lies inside the orbit. For stars in the outer regions of Andromeda, where most of the visible matter is far behind them toward the core, their orbital speeds should drop off significantly. They don't. They orbit much faster than they should, given the amount of visible matter. The math simply doesn't work. Those stars should have enough speed to escape the galaxy entirely, to fling themselves out into intergalactic space and never return. But they don't. They remain bound, moving in stable orbits as if held by gravity from something massive. Something invisible was keeping them tethered. The question was whether that something was real, or whether our understanding of gravity itself was incomplete. But that something is invisible. This is one of the strangest discoveries in modern astronomy. Not a dramatic event, but a persistent mismatch between what we see and what the motion implies must be there. It showed up first in the 1970s, when astronomer Vera Rubin measured rotation curves for spiral galaxies and found the same pattern repeated everywhere. Outer stars moving too fast, as if embedded in a halo of unseen mass. Andromeda shows it. The Milky Way shows it. Every large spiral galaxy shows it. Something is holding these galaxies together. Something with mass. Enough mass to dominate the gravitational field, but which emits no light, absorbs no light, and interacts with ordinary matter only through gravity. The visible galaxy, as magnificent as it is, 1 trillion stars, 220,000 light-years across, spiral arms and star-forming rings, and a supermassive black hole at its heart, represents only a fraction of Andromeda's true mass. Most of it is invisible, detectable only by the way it bends the trajectories of things we can see. Most of it is invisible, detectable only by the way it bends the trajectories of things we can see. So the question becomes unavoidable. In either our understanding of gravity is fundamentally wrong at galactic scales, or something invisible is present, something with mass, something that doesn't shine. For decades, both possibilities remained on the table. Maybe Newton and Einstein were right about gravity near planets and stars, but wrong when the distances stretched to hundreds of thousands of light years. Maybe the force weakens differently than we thought, or strengthens in ways our equations don't capture. Testing this required observations that didn't depend on rotation curves alone. Gravitational lensing provided the answer. When light from a distant galaxy passes near Andromeda, the path bends. Not much, just a subtle deflection, but enough to measure. The amount of bending depends only on mass. It doesn't matter if that mass glows or remains dark. His gravity curves space-time, and light follows the curvature. By measuring how much background galaxies appear distorted when viewed through Andromeda's gravitational field, astronomers could weigh the galaxy directly. No assumptions about orbital mechanics, no reliance on rotation speeds, just pure geometry. The measurements confirmed what the rotation curves suggested. The mass is far greater than the visible stars and gas can account for. 5 times greater, 6 times greater. The numbers vary depending on how far out you measure, but the conclusion is inescapable. Something is there, something that interacts with normal matter only through gravity. No light emitted, no light absorbed, no electromagnetic interaction of any kind. Just mass, just curvature. We call it dark matter, though the name is almost misleading. Yet it's not matter that happens to be dark, like a rock floating in space that no light shines on. It's matter that cannot emit or absorb light under any circumstances. It doesn't have electrons that can jump between energy levels. It doesn't form atoms in the way we understand atoms. It passes through electromagnetic radiation as if light doesn't exist. For every 1 kilogram of normal matter in Andromeda, every star, every planet, every atom of hydrogen drifting in the interstellar medium, there are roughly 6 kilograms of dark matter. The visible galaxy is not the main event. It's a trace contaminant. The stars we see, the spiral arms, the glowing core, all of it is just the luminous tip embedded in a vastly larger structure. The visible galaxy is just the beginning. Yes, so the dark matter halo extends at least 600,000 light-years from the center, nearly 3 times the diameter of the visible galaxy. Imagine an iceberg floating in the ocean. The part above water, white, gleaming, easily visible, represents perhaps 10 or 15% of the total mass. The vast bulk sits below the surface, invisible from above, but undeniably present. You can measure it by watching how the iceberg bobs in the waves, by the way currents deflect around it, by the ships that run aground on submerged ice they never saw. Andromeda is the tip, the part we photograph, the part that appears in images as a majestic spiral. It floats within an enormous invisible scaffold. The stars are decoration. The true structure is this dark matter halo, and the trillion suns we admire are merely the brightest fraction of something we mostly cannot see. The visible galaxy is just the beginning. What dark matter actually is remains one of the biggest mysteries in physics. The leading candidates have names. WIMPs, which stands for Weakly Interacting Massive Particles, and axions, hypothetical particles so light and ghostly they make neutrinos seem heavy by comparison. Experiments deep underground, shielded from cosmic rays, wait in silence for a dark matter particle to collide with a detector nucleus. So far, nothing definitive. The particles, if they exist in the forms we imagine, are extraordinarily shy. They pass through ordinary matter, almost without noticing it's there. Trillions of them could be moving through your body right now, and you would never know. But we detect dark matter, not by what it is, but by what it does. It holds galaxies together. It bends light. It shapes the large-scale structure of the universe, the cosmic web of filaments and voids that stretches across billions of light years. We know it's there, the way you know the wind is real. You can't see the wind. You see leaves moving, branches swaying, clouds racing across the sky. The wind is invisible, but its effects are undeniable. Dark matter is the wind that shapes galaxies. But even knowing dark matter exists, even measuring its distribution, we've still only seen Andromeda through the narrowest slice of reality. Visible light, the light our eyes evolved to detect, covers wavelengths from about 400 nanometers to 700 nanometers. And the full electromagnetic spectrum spans from gamma rays with wavelengths smaller than an atom to radio waves longer than a football field. Andromeda exists across all of it, and each wavelength reveals a different layer of the galaxy's anatomy. In radio wavelengths, Andromeda reveals vast clouds of cold, neutral hydrogen. This hydrogen emits a specific wavelength, 21 centimeters, when the electron, in a hydrogen atom, flips its spin relative to the proton. It's an extraordinarily gentle transition, releasing almost no energy, but there's so much hydrogen in the galaxy that the cumulative glow is detectable across millions of light years. Radio telescopes map this emission, tracing the raw material for future star formation. The hydrogen clouds extend beyond the visible disk, swirling in the halo, or orbiting in patterns that reveal the galaxy's rotation and structure in ways optical light cannot. In infrared, warm dust glows. Star formation heats the surrounding dust, tiny grains of silicates and carbon compounds, raising their temperature to 10 or 30 degrees above absolute zero. That's still unimaginably cold by human standards, but warm enough to emit infrared radiation. Telescopes like Spitzer and Herschel have mapped Andromeda in infrared, revealing dense clouds where stars are being born right now, hidden behind veils of dust that visible light cannot penetrate. In ultraviolet, young massive stars shine with ferocious intensity, each wavelength a different story, each frequency revealing what the others cannot. These stars, hot, blue, short-lived, pour out ultraviolet radiation that ionizes the gas around them, creating glowing nebulae. UV maps of Andromeda pinpoint the locations of recent star formation, highlighting the spiral arms where density waves trigger collapse and ignition. In X-rays, Andromeda reveals violence. X-ray binaries, systems where a neutron star or black hole strips matter from a companion star, heat the stolen gas to millions of degrees as it spirals inward. The gas glows in X-rays, betraying the presence of compact objects we could never see directly. Supernova remnants glow in X-rays too, expanding shells of debris from exploded stars, still hot from the shock of detonation, plowing through the interstellar medium at thousands of kilometers per second. Each wavelength peels back a different layer, revealing gas, dust, heat, and violence we could never see with our eyes alone. And within all these layers, stars live and die, each life contributing to the galaxy's slow transformation. Stars form in collapsing molecular clouds, regions where gravity finally overcomes the gas pressure that normally resists collapse. The minimum mass for a stable star, one capable of sustaining hydrogen fusion in its core, is about 8 times 10 to the 28th kilograms, roughly 40% the mass of the Sun. Below that threshold, you get a brown dwarf, an object that glows faintly from gravitational compression but never ignites true fusion. These failed stars drift through the galaxy, cooling slowly over trillions of years. Red dwarfs, the smallest true stars, burn hydrogen so slowly they can live for trillions of years, longer than the current age of the universe. Every red dwarf that has ever formed is still alive, is still fusing hydrogen in its core, still glowing with the same dim, patient light it had at birth. None have yet died of old age. The universe isn't old enough. Massive stars live fast and die young. A star 10 times the mass of the Sun burns through its hydrogen in just a few million years. It then fuses helium into carbon and oxygen, carbon into neon and magnesium, neon into silicon, silicon into iron. Each stage proceeds faster than the last. Hydrogen fusion lasts millions of years. Silicon fusion lasts days. When the core becomes iron, fusion stops. Iron doesn't release energy when it fuses. It absorbs energy. The core, no longer supported by fusion pressure, collapses in less than a second. The outer layers, suddenly unsupported, fall inward and rebound off the incompressible core. The star explodes, a supernova. The explosion is so violent, so energetic, that it creates elements heavier than iron, gold, platinum, uranium, through rapid neutron capture in the shockwave. These elements, along with all the lighter elements forged in the star's core during its life, scatter across space. Carbon, oxygen, nitrogen, silicon, iron, the building blocks of planets, the raw materials for life. This is how galaxies build complexity. Through the death of stars, the galaxy enriches itself, generation after generation. Early in Andromeda's history, more than 10 billion years ago, stars were made almost entirely of hydrogen and helium. These population 3 stars, as they're called, contained virtually no heavy elements because no previous generation had existed to create them. They ignited, burned, exploded, and seeded the interstellar medium with the first metals, where metals, in astronomical terms, means anything heavier than helium. The next generation, population 2 stars, formed from gas enriched by the deaths of their predecessors. They contained perhaps 0.1% heavy elements by mass, still almost pure hydrogen and helium, but with a trace contamination of carbon, oxygen, iron. These stars are old now, 12 billion years, some of them, and they populate the halo and globular clusters, orbiting far from the galactic plane in elliptical paths that carry them through the disk twice per orbit. Andromeda has about 450 globular clusters, dense spheres of hundreds of thousands of ancient stars, each cluster a relic from the galaxy's youth. They shine with a yellow-orange glow, the collective light of old, cool stars that have burned for eons. No young stars exist in globular clusters. A star formation ended there billions of years ago, when the gas was consumed or expelled. What remains are the survivors: red giants, white dwarfs, stars like the Sun entering their twilight years. Today's young stars, population 1 stars, contain about 2% heavy elements by mass. 2%. It sounds negligible, but it's enough to change everything. That 2% allows dust grains to form in stellar nurseries, and dust grains are what allow gas clouds to cool and collapse into stars in the first place. That 2% condenses into rocky planets orbiting young stars. That 2% includes every atom in your body, every breath of oxygen, every calcium atom in your bones, every iron atom in your blood. You are made of stardust, not as metaphor, as inventory, as atomic history, not poetically, literally. The atoms that make up your body were forged in the cores of massive stars that exploded billions of years ago, scattering their enriched ashes across the galaxy. Those atoms drifted through space, mixed with hydrogen and helium, condensed into a new generation of stars, and eventually, through a process so unlikely and so specific that it borders on the miraculous, assembled into a configuration capable of contemplating its own origin. That's what the 2% means. And the process continues. Andromeda forms roughly 1 solar mass worth of new stars every year. Over 1 billion years, that's 1 billion new stars. Not all at once. Star formation happens in bursts, clustered in spiral arms and star-forming rings, triggered by density waves and collisions between gas clouds. But the average rate, smoothed over time, is about 1 sun per year. Simultaneously, old stars die. Red giants shed their outer layers as planetary nebulae, glowing shells of gas expanding into space, lit from within by the dying core. Massive stars explode as supernovae, 2 or 3 per century in a galaxy the size of Andromeda, each one briefly outshining the entire galaxy in certain wavelengths. White dwarfs cool slowly, fading from white to yellow to red to black over trillions of years. Neutron stars spin in the darkness, their magnetic fields sweeping beams of radiation across space like cosmic lighthouses. The galaxy is not static. It is a constant cycle of birth, death, and chemical enrichment. The spiral arms we see in photographs are not permanent features, but waves passing through a sea of stars. Yes, the stars themselves are not eternal, but temporary. Lights that ignite, burn, and fade, each one contributing a small fraction of enriched material to the next generation. Galaxies grow by violence. Destruction creates the building blocks of planets and life. All of this, dark matter halos, hydrogen clouds, infrared glow, ultraviolet flares, X-ray binaries, supernova remnants, the slow enrichment of the interstellar medium with heavy elements, is invisible to the naked eye. The fuzzy patch you can barely see on a dark night, the smudge that drew ancient astronomers to wonder what it was, hides unimaginable complexity. Every photon that reaches your eye from Andromeda carries information, but only about a narrow slice of reality. The rest requires instruments, radio dishes, infrared telescopes, X-ray satellites, and even then, yet we see only the matter that interacts with light. The dark matter, the true bulk of the galaxy, remains hidden. So Andromeda, as vast as it appears, is just the glowing heart of an even larger invisible structure. And it is not alone. It is surrounded by smaller galaxies, dozens of them, many of which orbit Andromeda like moons orbiting a planet. Some of these satellites are intact, small elliptical galaxies and dwarf spheroidals that have survived billions of years in Andromeda's gravitational grip. Others are not so lucky. Tidal forces stretch them, tear them apart, and gradually fold their stars into Andromeda's halo. The evidence of this consumption is visible in long streams of stars arcing through the outer regions of the galaxy. Tidal streams, the remnants of smaller galaxies that no longer exist as coherent objects. These tidal streams are not random scatter. They are fossils. The stretched remains of smaller galaxies that Andromeda consumed long ago, stars pulled into elongated orbits by tidal forces so vast they ripped entire systems apart over hundreds of millions of years. The streams wrap around the galaxy in shells and arcs, some extending hundreds of thousands of light years from the galactic center. They persist for billions of years, stars slowly spreading out along their orbits, each one a breadcrumb marking the path of a galaxy that no longer exists. Each stream is a timeline written in stars, a fossil record not of bones, but of motion. This is not ancient history preserved in stone. This is ongoing digestion. The streams are still there, still visible, still spreading, and a slow-motion record of destruction playing out across timescales so long that entire stellar civilizations could rise and fall between one orbit and the next. Galaxies grow by violence. Galaxies grow by violence. Not in sudden cataclysmic bursts, though those happen too, but in slow consumption, in gravitational predation that takes billions of years to complete. Andromeda does not orbit alone. It is surrounded by at least 14 known satellite galaxies, small systems gravitationally bound to it, trapped in orbits they cannot escape. Some of these satellites are intact, for now. Others are being torn apart as we observe them. 2 stand out as particularly prominent, visible in amateur telescopes as faint companions flanking the galaxy itself. M32 sits just 24,000 light-years from Andromeda's center, and that's closer than the Sun is to the center of the Milky Way. M32 is small, about 8,000 light-years across, but dense, compressed. It contains a surprisingly massive black hole at its core, between 2 and 4 million solar masses. That's comparable to Sagittarius A star, the black hole at the heart of our own galaxy, despite M32 being a fraction of the Milky Way's size. This suggests M32 was once much larger. Something stripped away its outer layers. Something tore through its spiral arms and scattered its stars, leaving only the dense core behind. That something was Andromeda. This is what satellite galaxies are, not companions, but victims in various stages of consumption. M110 lies farther out, about 170,000 light-years from Andromeda's center. Yet it's a dwarf elliptical galaxy, a smooth oval of old stars with no gas, no dust, no star formation, just ancient suns slowly fading, orbiting a galaxy that will eventually consume them. Both M32 and M110 are visible as small, fuzzy patches near Andromeda in photographs. Companions. But that word suggests equality, partnership. These are not independent galaxies choosing to orbit nearby. They are prisoners, slowly being torn apart by Andromeda's gravity. Over the next few billion years, their stars will be absorbed into Andromeda's halo, adding to the diffuse glow of the outer galaxy. The satellites themselves will cease to exist as distinct objects. This is how large galaxies grow, not through internal processes alone, through star formation and stellar evolution, but through external acquisition. As through cannibalism, the mechanism is tidal force. Andromeda's gravity is not uniform. The near side of a satellite galaxy feels stronger pull than the far side. This difference, this gradient, stretches the satellite along the axis pointing toward Andromeda. Over millions of years, the stretching becomes severe. Stars on the near side accelerate toward Andromeda. Stars on the far side lag behind. The galaxy elongates, distorts, and eventually comes apart. Its stars don't disappear. They continue orbiting Andromeda, but now as individual objects rather than as part of a coherent system. They form long streams, ghostly trails marking the path of the satellite's orbit. Some streams contain thousands of stars. Some contain millions. All of them are remnants. Andromeda's stellar halo extends at least 500,000 light-years from the galactic center, perhaps farther. The halo's outer boundary is difficult to define because the stars become so sparse they blend into the background. The halo contains about 1% of the galaxy's total stars, a small fraction. But spectroscopic analysis reveals something crucial. Those stars didn't form in the halo. They came from multiple smaller galaxies, torn apart over billions of years and folded into Andromeda's outer structure. Each stream, each shell, represents a separate event, a separate victim. The visible galaxy is just the beginning. What we see in photographs, the bright disk, the spiral arms, the central bulge, is only the active, luminous core. The halo is a graveyard, not a place where galaxies died quickly, a place where they died so slowly their deaths are still visible, still happening, spread across time so vast it looks like stillness, evidence of past violence preserved in the orbits of scattered stars. And there's something strange about Andromeda's satellites. Many of them orbit in a thin plane, rather than being randomly distributed in a three-dimensional sphere around the galaxy. This is unexpected. If satellites formed independently and were captured over time, you'd expect them to orbit in all directions. Random angles, random inclinations, but a significant fraction orbit in roughly the same plane, like planets around a star. This suggests they didn't form independently. They formed from debris. The leading explanation is that a large galaxy collided with Andromeda 8 to 10 billion years ago. And not a glancing blow, a major merger. The collision destroyed both galaxies as coherent spiral systems and triggered a massive burst of star formation as gas clouds collided and compressed. Over time, the two galactic cores spiraled inward and merged. But the debris from the collision, gas, stars, dark matter, was flung into orbits around the merged galaxy. That debris coalesced. It formed new, smaller systems. The satellites we see today may be the descendants of that ancient collision, still orbiting in the plane where the impact occurred. This is not the only merger Andromeda has experienced. A more recent event happened roughly 800 million years ago. That collision significantly disrupted Andromeda's spiral arms and triggered another burst of star formation. But we can see the evidence in the age distribution of stars. Certain regions contain clusters of stars all born around the same time, consistent with a sudden influx of gas compressing and igniting. So, Andromeda didn't form peacefully. It grew by cannibalizing its neighbors, and that process continues today. This is hierarchical assembly, the dominant paradigm of galaxy formation. The process has a name because it is universal. What happened to Andromeda happened everywhere. Small density fluctuations in the early universe, just tens of millions of years after the Big Bang, collapsed under gravity to form the first tiny galaxies. Those galaxies merged to form larger galaxies. Those larger galaxies merged to form still larger galaxies. The process cascades upward, building structure through collisions and consumption, or all the way to the massive spiral galaxies we see today. Andromeda is the product of countless mergers. Galaxies grow by violence, hundreds, thousands perhaps. Each satellite it consumed added mass, added stars, added angular momentum. Each merger changed the galaxy's shape, redistributed its gas, triggered new waves of star formation. The galaxy we see now is not a pristine object that formed intact. It is a composite, an accumulation of everything it has devoured over 13 billion years. And it is not unique. The Milky Way is the same. Both are large spiral galaxies. Both are dominated by dark matter. Both have massive black holes at their centers. Both have extensive satellite systems. Both are apex predators in their local environment, actively consuming smaller neighbors. The similarities are striking. Andromeda is somewhat larger. Its disk spans roughly 220,000 light-years in diameter, compared to the Milky Way's 100,000 light-years. Andromeda contains approximately 1 trillion stars. The Milky Way contains somewhere between 100 billion and 400 billion. The uncertainty reflects the difficulty of counting stars from inside the galaxy. In terms of total mass, including dark matter, both galaxies weigh roughly the same, between 1 and 2 trillion solar masses. There was a debate in 2018 and 2019, sparked by new measurements of the Milky Way's dark matter halo, suggesting our galaxy might actually be heavier than Andromeda. Subsequent analyses walked those claims back. The current consensus places them roughly equal, with Andromeda perhaps slightly more massive. Both galaxies have large satellite populations. Andromeda has at least 14 confirmed satellites. The Milky Way has over 50, including the Large and Small Magellanic Clouds, 2 irregular dwarf galaxies visible from the southern hemisphere, bright enough to be mistaken for detached pieces of the Milky Way itself. These satellites are not permanent companions. The Magellanic Clouds are slowly being pulled toward the Milky Way. In a few billion years, they will be absorbed, just as M32 and M110 will be absorbed into Andromeda. The violence is not exceptional. It is universal. Every large galaxy grows this way. These are not just neighbors. They are twins, both dominant, both violent, both hurtling toward each other. Because Andromeda and the Milky Way do not exist in isolation, they are the 2 dominant members of the local group, a collection of roughly 50 galaxies spanning about 10 million light-years. The local group is gravitationally bound. It is not expanding with the universe. Cosmological expansion applies at much larger scales, between galaxy clusters, between superclusters. But within a gravitationally bound system like the local group, the mutual attraction of the member galaxies overcomes the expansion. They orbit a common center of mass. Andromeda and the Milky Way collectively contain over 90% of the local group's mass. The third largest member, the Triangulum galaxy, also known as M33, is much smaller, with perhaps 40 billion stars. It may itself be a satellite of Andromeda, caught in a long elliptical orbit. The rest of the group consists of dwarf galaxies, small, faint, mostly dark matter-dominated systems with a few million to a few billion stars each. The local group is not a democracy. It is a hierarchy. 2 massive galaxies dominate. Everything else orbits, waits, or falls. And those 2 massive galaxies are moving toward each other. Andromeda and the Milky Way orbit their common center of mass, but the orbit is not stable. The gravitational attraction between them is immense, far stronger than the tangential velocity that might allow them to orbit indefinitely. They are falling toward each other at approximately 110 kilometers per second. That's 68 miles per second, 400,000 kilometers per hour, 250,000 miles per hour. Now, these numbers stop meaning anything after a while. The mind cannot hold speeds like this. At that speed, you could circle Earth's equator in just over 6 minutes. You could travel from the Earth to the Moon in about an hour. It is faster than any human-made object has ever traveled, faster than the Voyager probes, which are currently humanity's most distant spacecraft, coasting through interstellar space at a fraction of that velocity. But despite this speed, the two galaxies are still so far apart that they are only closing the gap by about 100 light-years every million years. 100 light-years. That's roughly the distance from the Sun to a few hundred of its nearest stellar neighbors, a trivial distance on the scale of a galaxy. Every million years, the gap shrinks by that amount, and it sounds fast and slow at the same time. Fast because 110 kilometers per second is incomprehensibly rapid by human standards. Slow because even at that speed, it will take billions of years for the galaxies to collide. Space is so vast that even fast motion appears slow. This is the paradox of astronomical velocity. Objects moving at speeds that would vaporize anything on Earth, speeds that represent staggering kinetic energy, drift across the sky so slowly that their motion is invisible over human lifetimes. Andromeda's position in the sky has not changed noticeably in recorded history. It will not change noticeably for thousands of years to come, but it is moving. Every second, it closes 110 kilometers. Every year, 3.5 billion kilometers. Every million years, 100 light years. And this approach is inevitable. Gravity is pulling the galaxies together. There is no force opposing it. Cosmological expansion is irrelevant at this scale. The local group is too small, too tightly bound for the expansion of space to counteract gravity. The collision is certain, not likely, not probable, certain. The math allows no other outcome. There is no escape, no intervention possible. Just gravity doing what gravity does, pulling mass toward mass, accelerating objects along the curvature of space-time, indifferent to the complexity of what it draws together. We are seeing Andromeda not as it is, but as it was, 2.5 million years ago. The light we observe left Andromeda before modern humans existed, before Homo sapiens walked out of Africa, before stone tools became widespread. By the time that light reached Earth, here crossing the vast emptiness between galaxies, our species had emerged, built civilizations, developed writing, mathematics, telescopes. We captured the light and calculated backward, reconstructing the galaxy's motion through space. And we discovered that it is heading directly toward us. We can model this collision. Supercomputers run simulations, tracking billions of particle trajectories under mutual gravitational influence. The simulations incorporate dark matter, gas dynamics, star formation, black hole interactions. This is how we know what will happen 4 billion years from now. Not prophecy, but physics. They predict the timeline, the stages, the final outcome. The calculations are robust, consistent across multiple research groups using different models. The details vary slightly, but the broad strokes are clear. Roughly 4.5 billion years from now, the two galaxies will have their first close encounter. 4.5 billion years. That's the timeline. The first close encounter. And there's something almost poetic about this timing. 4.5 billion years from now, our Sun will be nearing the end of its main sequence life. It will have exhausted most of the hydrogen in its core. The balance between gravity and fusion pressure will shift. The core will contract, heating up, and the outer layers will expand dramatically. The Sun will swell into a red giant, perhaps large enough to engulf Mercury and Venus entirely. Earth will not be swallowed, probably, but it won't matter. The surface temperature will rise to thousands of degrees. The oceans will boil away. The atmosphere will be stripped into space. Earth will be sterilized, a dead rock orbiting a dying star. So humans, in our current form, will not witness the merger. We will be gone. Our species, our civilizations, our monuments, all of it erased long before the galaxies collide. But if any descendants survive elsewhere, on distant worlds, in artificial habitats, in forms we cannot currently imagine, this is what they will see. The first pass will not be gentle. As the two galaxies swing past each other, tidal forces will pull out long streamers of stars and gas, massive tidal tails stretching millions of light years into space, glowing with newly triggered star formation as gas clouds collide and compress. Galaxies grow by violence. The collision will scramble the ordered spiral arms, flinging stars into chaotic new orbits. From a planet in either galaxy, the night sky will be transformed, no longer a faint smudge in the distance. Instead, the approaching galaxy will dominate the view, a sprawling, distorted structure filling half the sky, glowing gas, brilliant blue star clusters, the twisted wreckage of both galaxies stretched and warped by gravity. It will be beautiful, chaotic, catastrophic, and magnificent all at once, and no one will see it. Not us. Not anyone we could possibly be related to. The most spectacular event in our cosmic neighborhood will unfold long after our lineage has ended. We can model it. We can simulate it. We can predict it with extraordinary precision. But we cannot witness it. The universe does not arrange its schedule for our convenience. After the first pass, the galaxies will not merge immediately. They will swing back toward each other, orbiting their common center of mass, multiple passes over the next 1 to 2 billion years. Each time they approach, gravitational interactions will sap energy from their motion, not friction. There is no medium to create friction in the vacuum of space, but gravitational interactions redistribute energy, transferring momentum between stars and gas clouds and dark matter. With each pass, the galaxies lose orbital energy and spiral closer. Finally, roughly 3 to 5 billion years after the first encounter, the two galaxies will merge completely. The final state will be a single, giant elliptical galaxy, 1.5 to 2 trillion stars, playfully nicknamed Milk-Dromeda by astronomers who appreciate a good portmanteau. The ordered spiral structure of both galaxies will be gone, scrambled. In stars will orbit in random directions, forming a smooth, featureless, elliptical blob. No more spiral arms, no more disk, just a vast, three-dimensional swarm of stars moving in chaotic orbits around a common center. And at that center, something extraordinary will happen. The two supermassive black holes, 140 million solar masses from Andromeda, 4 million solar masses from the Milky Way, will themselves spiral together and merge. This will not happen quickly. Even after the galaxies merge, the black holes will take hundreds of millions of years to find each other. They will drift toward the center of the merged galaxy, pulled by dynamical friction, a process where their gravitational influence slows them down as they scatter nearby stars. Eventually, they will form a binary system, orbiting each other at closer and closer range. And then they will merge. The collision will release a tremendous burst of gravitational waves, more energy than all the stars in the observable universe emit as light, combined, radiated in the span of a few seconds. Not as light, not as heat, as ripples in space-time itself. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves for the first time. Two black holes, each about 30 times the mass of the Sun, spiraled together and merged 1.3 billion light-years away. The waves traveled across the universe, stretching and compressing space-time as they passed. When they reached Earth, they distorted the fabric of reality by a distance smaller than a proton, but LIGO detected it. That detection confirmed a century-old prediction by Einstein. It opened an entirely new way of observing the universe, not through light, but through gravity itself. The merger of Andromeda's and the Milky Way's black holes will be far more powerful, thousands of times more massive. The gravitational waves will be proportionally stronger. If any civilization exists in the local group at that time, and if they have instruments like LIGO but scaled up, they will detect a signal of staggering intensity, a cosmic event written in the curvature of spacetime. Gravity itself will ring like a bell, and the sound will travel forever. But here's the paradox. Calling it a collision is misleading. Stars are so far apart that the probability of two stars physically colliding during the merger is almost zero. And a star is roughly 1 million kilometers across. The distance between stars is measured in light years, trillions upon trillions of kilometers. A star is like a grain of sand. The space between stars is kilometers of emptiness. When the galaxies pass through each other, it will be like two clouds of smoke interpenetrating. Individual solar systems will be flung into new orbits, sometimes ejected from the galaxy entirely, cast into the intergalactic void. But the stars themselves will remain intact. Planets will continue orbiting their suns. Any hypothetical observers on those planets will see the sky change. new constellations, new structures, but their own solar system will survive unscathed. The gas clouds, however, will collide. Gas is more diffuse than stars, spread across vast regions. But there is enough of it that when two galaxies merge, their gas clouds slam into each other. The collisions compress the gas. Compressed gas collapses under its own gravity. Collapsed gas ignites into new stars. The merger will trigger intense bursts of star formation. Short-lived, but spectacular. Millions of massive, hot, blue stars will be born in a span of just a few 100 million years. These stars will live fast and die young, supernovae detonating across the merged galaxy, seeding space with heavy elements, leaving behind neutron stars and black holes. But over billions of years, the gas will be used up or expelled. Stellar winds and supernova explosions will blow much of it out of the galaxy entirely. Star formation will cease. The merged galaxy will become what astronomers call red and dead, dominated by old, cool, red stars. No young blue stars being born, just the slow fade of a galaxy that has exhausted its fuel. So the two galaxies we see today, separate, ordered, majestic, will eventually become a single chaotic swarm of stars. The visible galaxy is just the beginning. What we observe now is a snapshot, a moment in a process that spans billions of years. The galaxies are not static. They are evolving, merging, transforming into something new. And through all of this, through the collision, the merger, the scrambling of orbits, and the bursts of star formation, individual worlds will endure, which raises a question. With 1 trillion stars in Andromeda, how many planets must it contain? We don't have to guess. We have data. NASA's Kepler mission, launched in 2009, spent years staring at a single patch of sky, here monitoring the brightness of over 150,000 stars. It was looking for planets. Specifically, it was looking for the tiny dip in brightness that occurs when a planet passes in front of its star, blocking a fraction of the light. Kepler found thousands of planets, and the data revealed something profound. Planets are the rule, not the exception. Most stars have planets, not some, most. Conservative estimates, based on Kepler's data and follow-up surveys, suggest at least one planet per star on average. Many stars have multiple planets, some have none, but averaged across the galaxy, the ratio is roughly 1:1. So Andromeda, with 1 trillion stars, likely hosts around 1 trillion planets. Let that settle, 1 trillion worlds. The number is too large to hold, but it sits there, is solid as mathematics can make it. Not stars, worlds, places with surfaces, with weather, with geology, with histories we will never know, rocky planets, gas giants, ice worlds, lava planets orbiting close to their stars, frozen planets in the outer reaches of their systems, rogue planets ejected from their birth systems, drifting alone through interstellar space. Many of these will be Earth-sized. Many will orbit in their star's habitable zone, the region where temperatures allow liquid water to exist on the surface. The numbers are staggering. Even if only 1% of stars have habitable zone planets, a conservative estimate, that's 10 billion candidates. If only 1% of those develop life, that's 100 million living worlds. The statistics are overwhelming. The visible galaxy is just the beginning. As we see stars, we infer planets. Behind the light, hidden in the shadows of distant suns, are worlds we cannot directly observe, but know must exist. The visible galaxy is just the beginning, another layer of complexity, another scale of structure beyond what we can see. This is not speculation. The math is clear. We have gone from searching for planets to counting them in the trillions. In less than 2 decades, we learned the universe is fuller than we imagined. Andromeda is almost certainly alive. On Earth, life appeared roughly 3.8 billion years ago, just 700 million years after the planet formed, after the late heavy bombardment ended, after the surface cooled enough for liquid water to persist. Life arose quickly, and it has persisted through mass extinctions, climate shifts, asteroid impacts, air gamma ray bursts from nearby supernovae. It survived snowball Earth events, where the entire planet froze over. It survived the Permian extinction, which killed 90% of all species. This is still about Andromeda, about what might be possible there, given what we know from here. This suggests something important. Given liquid water, organic chemistry, and an energy source, Life is not a miracle. It is nearly inevitable, and the ingredients are common. Water exists throughout the galaxy. Comets are made of ice. Moons of Jupiter and Saturn have subsurface oceans. Molecular clouds contain water molecules frozen onto dust grains. Organic molecules, the carbon-based building blocks of life, are abundant in space. Amino acids have been found in meteorites. Complex organic compounds form in the atmospheres of planets and in the shells around dying stars, in the cold depths of molecular clouds. Stars provide energy. Every star is a fusion reactor, pouring light and heat into the surrounding space. And where there is liquid water and energy, chemistry happens. Molecules collide, bond, break apart, reassemble. Complexity builds. So Andromeda almost certainly hosts countless microbial biospheres. Somewhere, on some rocky world orbiting some unremarkable star in one of its spiral arms, there are organisms. Simple, single-celled, struggling to survive, evolving, adapting. Right now, as you listen to this, as you drift towards sleep, there are likely billions of living organisms under alien skies. But life and intelligence are not the same thing. Different biochemistry, perhaps. Different genetic codes. Different evolutionary pressures. But alive. And this is what the numbers tell us. This is what the evidence from Earth suggests. Life is not rare. It is common. But intelligence is a different question. Life on Earth remained simple for 3 billion years. Single-celled organisms. Bacteria and archaea. No eyes. No brains. No awareness. Complex life, multicellular organisms with specialized tissues, took another 500 million years to emerge. Intelligence took even longer. Brains capable of abstract thought, language, tool use. These appeared only in the last few million years. And technological civilization, capable of building telescopes, transmitting radio signals, leaving the planet, has existed for only about 100 years. A blink in cosmic time. Less than 1/1,000,000th of 1% of Earth's history. Intelligence, it seems, is not inevitable. It is fragile, a recent accident in a very old story. So even if life is common, intelligence might be rare, very rare. The Fermi paradox looms over this question. If intelligent civilizations are common, where are they? Why haven't we detected them? Why isn't the galaxy filled with radio signals, megastructures, self-replicating probes exploring every star system? Possible explanations multiply. Maybe intelligence is rare. Maybe the jump from simple life to complex life is the hard step. Or the jump from complex life to intelligence. Or the jump from intelligence to technology. Maybe civilizations self-destruct quickly. Nuclear war, environmental collapse, runaway artificial intelligence. Maybe the gap between developing technology and destroying yourself is measured in centuries, and we're currently in that gap. And maybe they stay deliberately silent. Broadcasting your presence might be dangerous. The dark forest theory suggests that any civilization revealing itself risks attracting the attention of more powerful, hostile civilizations. So everyone stays quiet, listening, waiting. Maybe they lose interest. Maybe advanced civilizations retreat into virtual realities, building simulated worlds far richer than physical exploration. Why travel between stars when you can create entire universes inside a computer? Or maybe the galaxy is simply too vast. Even if thousands of civilizations exist right now, the distances between them might make contact vanishingly unlikely. Or perhaps we are, in fact, alone. Not alone in the sense that life is rare, but alone in the sense that intelligence and technology are so improbable, as so contingent on specific evolutionary pathways, that we are the only example in billions of light years. We don't know. The absence of evidence is not evidence of absence, but it is unsettling. Still, even if intelligent civilizations exist in Andromeda, thousands of them, right now, building telescopes and asking the same questions we ask, we will never know their present reality. We are seeing Andromeda not as it is, but as it was, 2.5 million years ago. The light we observe left before modern humans existed. Right now, in Andromeda's actual present, stars are being born, planets are forming, black holes are flaring, satellites are being ripped apart, and perhaps, just perhaps, civilizations are rising and falling. But we cannot see that present. If a civilization in Andromeda sends a signal today, yet we will not receive it for 2.54 million years. If we respond, they will not receive our reply for another 2.54 million years. The round-trip delay is over 5 million years, longer than our species has existed, longer than the entire genus Homo has existed. Even if we received a message tomorrow, a deliberate transmission, undeniably artificial, the civilization that sent it might be extinct by the time we reply. They might have destroyed themselves, evolved into something unrecognizable, transcended physical form, or simply lost interest and gone silent. We would be responding to ghosts. This is the prison of the speed of light, not just a speed limit, an isolation barrier. We are cut off from the galaxy's present. We see only the past. We can send messages into the future, but we can never hold a conversation, never exchange ideas in real time, never know what is happening right now on the other side of the void. The distance is not just spatial, it is temporal. We are not separated from Andromeda by 2.5 million light years. We are separated by 2.5 million years of time. The galaxy we see no longer exists in that form. It has already changed. Stars have died. New stars have been born. Civilizations, if they exist, have come and gone. And we will never catch up, no matter how long we wait, no matter how carefully we listen. The present of Andromeda will always be 2.5 million years ahead of us, forever out of reach. This is the loneliness built into the structure of space-time itself. So even if they exist, even if they are looking back at us right now, yet we are ghosts to each other, visible only in the past, never in the present. This is the profound loneliness of the universe at scale. Andromeda may be teeming with life, billions of organisms, thousands of civilizations, entire histories unfolding under alien suns. But we will die, individually and as a species, without ever knowing. The mathematics guarantee planets. The chemistry suggests life. The statistics hint at intelligence. But the speed of light ensures we remain alone. And Andromeda, for all its grandeur, for all its trillion stars and billion worlds, is just one galaxy, one island in an ocean of billions. And Andromeda, for all its grandeur, for all its trillion stars and billion worlds, is just one galaxy, one island in an ocean of billions. So let's place it in context. And let's zoom out one final time and see where it actually stands in the hierarchy of cosmic structures. Because for all its vastness, for all the incomprehensible distances and masses we've been circling, Andromeda is not even close to the largest galaxy in the universe. Not close. There are galaxies that dwarf it. IC 1011, a massive elliptical galaxy in the Virgo cluster, was once thought to span 6 million light-years across, nearly 3 times Andromeda's diameter. Later measurements revised that estimate downward to between 1 and 2 million light-years. But even at the lower end, the sheer scale remains staggering, and it contains an estimated 100 trillion stars, 100 times Andromeda's stellar population, 100 times a trillion. The number loses meaning. It becomes sound rather than quantity. Yet then there's Messier 87, M87. We are still placing Andromeda in context, seeing where it stands among the true giants. The giant elliptical at the heart of the Virgo cluster. It spans about 120,000 light-years, smaller in diameter than Andromeda, actually, but it contains a supermassive black hole weighing 6.5 billion solar masses, 46 times more massive than Andromeda's central black hole. In 2019, the Event Horizon Telescope captured the first direct image of this black hole's shadow, a glowing ring of light bent around the event horizon, the boundary beyond which nothing, not even light, can escape. The photograph showed us the edge of space-time itself, the place where physics as we understand it breaks down. Yea, the image traveled 55 million light-years to reach us. We were looking at the shadow of a monster. So Andromeda, vast as it is just one galaxy among billions. Neither the largest nor the smallest, but extraordinary nonetheless. The truth is, most galaxies in the universe are actually much smaller than Andromeda. Dwarf galaxies, tiny structures with only millions or billions of stars. The universe is filled with them, small, faint, easily overlooked. Andromeda and the Milky Way are in the top 5% by size. We live in a big galaxy, orbiting near an even bigger one. but the true giants dwarf them both, and even the local group, our little cluster of Andromeda, the Milky Way, Triangulum, and dozens of smaller galaxies, is just a minor structure, a small pond. And the local group is one of countless galaxy groups scattered through the cosmic web, that vast filamentary structure of matter that spans the observable universe. Galaxy clusters connected by tendrils of dark matter, with vast voids in between. Andromeda is a big fish in a small pond, and the pond itself is just one puddle in an endless landscape. The visible galaxy is just the beginning. Every structure contains a larger structure. Every answer reveals another question. We thought the Milky Way was the universe. Then we discovered galaxies beyond it. We thought Andromeda was incomprehensibly large. Now we know there are galaxies 100 times its size. The scaling never stops. But let's not lose Andromeda in the vastness. Let's return to it. Because even if it's not the largest, it has a history worth contemplating. Andromeda's earliest stars formed over 10 billion years ago, when the universe itself was less than a quarter of its current age. Those stars have been burning longer than Earth has existed, longer than our Sun has existed, longer than our entire solar system has existed. Think about that continuity. And the globular clusters orbiting in Andromeda's halo, those dense, spherical swarms of ancient stars we mentioned earlier, are fossils from the galaxy's youth, 12-billion-year-old time capsules. They formed when the universe was still young, still violent, still assembling its first large structures, and they have orbited silently, unchanged, through everything that followed, through the entire history of our solar system, through the formation of Earth, through the rise of life, the evolution of complex organisms, the emergence of intelligence, through every empire that has risen and fallen on our planet, through every thought any human has ever had. These stars existed before any of it. They witnessed the formation of everything we know, and they will continue to exist long after we're gone. Galaxies grow by violence, yes, but also by patience, by time, by the slow, grinding work of gravity over billions of years. The structure we see today is the result of 13 billion years of assembly, mergers, collisions, smaller galaxies torn apart and absorbed, dark matter halos collapsing under their own gravity, pulling gas inward, igniting new generations of stars, spiral arms forming from density waves, black holes growing at the center, feeding on infalling matter, all of it driven by gravity, all of it beginning from almost nothing. The seeds of Andromeda were planted in the early universe, in the tiny density fluctuations that existed just a few 100,000 years after the Big Bang, variations of just one part in 100,000 in the distribution of matter, regions where the density was slightly higher, slightly lower, quantum fluctuations, stretched to cosmic scales by the expansion of space itself. These fluctuations were imprinted in the cosmic microwave background radiation, the afterglow of the Big Bang, still visible today as faint radio waves filling the sky. Satellites like Planck have mapped these fluctuations in exquisite detail, our baby picture of the universe, the blueprint from which everything, galaxies, clusters, superclusters, would eventually grow. Andromeda began as one of these slight overdensities, a region where gravity pulled matter together just slightly faster than surrounding regions. Over hundreds of millions of years, this overdensity grew. Matter fell inward. The collapse accelerated. Dark matter collected first, forming the invisible scaffolding. Then gas followed, falling into the dark matter halo, heating up, her cooling down, fragmenting into clouds. And from those clouds, the first stars ignited. 13 billion years of gravity, and this is the result. A structure so vast we can barely comprehend it. But now, gently, let's shift our perspective, not toward new science, not toward additional facts about Andromeda's structure or history, but toward something quieter, something closer to us. We are standing on a small planet, orbiting an average star, in the outer suburbs of an unremarkable spiral galaxy. We are made of atoms forged in ancient stars that exploded billions of years ago. Carbon, nitrogen, oxygen, iron, calcium. Every element heavier than helium was created inside a star or during a supernova. We are, quite literally, made of stardust. Not metaphorically, literally. Our bodies are temporary. A typical human lifespan is 80 years. maybe 90. A blink against the timescales we've been discussing. Less than 1/1000th of Andromeda's age. Less than 1/10,000,000th of the universe's age. Our species is even younger. Modern Homo sapiens has existed for perhaps 300,000 years. Anatomically modern humans, behaviorally modern humans, capable of language, art, abstract thought, for maybe 50,000 years, and technological civilization, the ability to build telescopes, measure distances, map galaxies, barely a century, 100 years out of 13 billion. And yet, from this tiny, fleeting vantage point, we have mapped a galaxy 2.54 million light-years away. We have counted its stars. We have measured its mass. We have predicted its future collision with our own galaxy. We have inferred the existence of invisible matter holding it together. Matter we cannot see, cannot touch, cannot directly detect. We have calculated the planets it must contain. We have contemplated the lives it might host. We are seeing Andromeda not as it is, but as it was. And now, after this journey, we understand the full weight of that truth. Not just that the light is old, but that simultaneity itself is an illusion. That the present moment in Andromeda is forever beyond our reach. That we are separated not just by space, but by time. That even if civilizations exist there right now, we will never share a moment with them. We are ghosts to each other, visible only in the past. This understanding, this mapping of something so distant and ancient, is extraordinary. Not because Andromeda is special, but because we can grasp it. Yet the universe did not design us to understand galaxies. Evolution shaped our brains to find food, to recognize patterns in animal tracks and weather and the behavior of other humans, to avoid predators, to cooperate socially, to navigate a landscape of savannas and forests and rivers. Nothing about survival on the African savanna required comprehension of trillion-star islands millions of light-years away. Nothing about hunting or gathering or raising children demanded that we develop mathematics capable of mapping invisible dark matter, or calculating gravitational orbits, or predicting cosmic collisions billions of years hence. And yet, here we are. Our pattern recognition, evolved to track animals and predict seasons, can also grasp density waves and spiral arm dynamics. Our social intelligence, evolved to navigate human relationships and detect deception and build alliances, can also construct the cosmic distance ladder. The same neural architecture that learned to nap stone tools and control fire has learned to map the structure of galaxies we can barely see with the naked eye. This is improbable. Evolution is blind. Selection is random. Mutations are accidents. There is no forward planning, no designer steering us toward cosmic awareness. Our brains are the result of millions of generations of survival pressure. Hunt better, communicate better, cooperate better, survive long enough to reproduce. That's it. That's all natural selection cares about. The fact that this process, blind, random, indifferent, produced minds capable of understanding galaxies is not guaranteed. It is not necessary. And most species never develop this capacity. Most never will. And yet, it happened. By pure accident, the cognitive tools we developed for survival on one small planet turned out to be general enough, powerful enough, to comprehend the cosmos that made them. The atoms in our bodies have, through billions of years of cosmic evolution, arranged themselves into structures capable of contemplating the cosmos. Hydrogen atoms, forged in the Big Bang. Carbon atoms, created in dying stars. Oxygen, silicon, iron, all assembled over generations of stellar life cycles. And now, on at least one small world, these atoms have organized themselves into brains, into minds, into consciousness. We are the universe becoming aware of itself. Andromeda exists whether we understand it or not. It would still be there, still spinning, still growing, and still preparing for its eventual merger. Even if no conscious being ever looked at it, the trillion stars would burn. The dark matter would hold it together. The spiral arms would wind and unwind. None of it requires our observation. But the fact that we do understand it, even partially, even imperfectly, is perhaps the greatest mystery of all. Not the size of the galaxy, not the distance, not even the dark matter or the coming collision. The mystery is understanding itself. The mystery is that a species that has existed for a cosmic eye blink on a world that is less than a mote of dust in the cosmic ocean can look up at a faint smudge of light and know what it is, can measure it, can map it, can predict its future, can hold in our minds, briefly, imperfectly, but genuinely, a structure so vast it makes our entire world invisible. Tonight, if you step outside, you can see Andromeda with your own eyes. If the sky is dark enough, if you know where to look, a faint smudge of light between Cassiopeia and Pegasus, easy to miss, easy to mistake for a cloud. That light is 2.54 million years old. It left Andromeda before modern humans existed, before Homo erectus, before our entire lineage split from other hominins. The photons hitting your eye tonight began their journey across the void when our ancestors were still small apes in African forests. A trillion stars compressed into a faint glow, and you, an improbable arrangement of atoms on a tiny world, alive for a brief span of time, conscious for reasons no one fully understands, can look up at that light and know what it is. Yet that is the true scale of Andromeda, not its distance or its mass, not the billion worlds it likely contains or the civilizations it might host. The true scale is the distance across which understanding can reach. The universe is vast, ancient, mostly indifferent to our existence. We are brief, fragile, confined to one small world orbiting one ordinary star in the outer reaches of one unremarkable galaxy. But the universe is also, through us, capable of wonder, and that wonder, brief and fragile as it is enough.